So a quick overview on Spark. It's relatively young. It came out of a 2010 paper from Berkeley's MLab. And I highly encourage everyone to read the paper. But the gist of it is, it describes an abstraction called resilient distributed data sets, or RDDs for short. And well, this talk will be about RDDs, so I'll wait to elaborate on it. But going more on Spark, so Spark builds a generalized distributed computation engine and platform based on the concept of RDDs. And what's unique about Spark is that you have fault-tolerant in-memory caching, so that data can be shared in between workloads in a really fast manner, instead of having to read out of a network store such as HDFS. But also the big win of RDDs is that it offers a more expressive API where other systems can build upon to really create nice interfaces to support various workloads such as graph analysis or streaming or SQL. So Spark is really split into two different pieces. One is the core, which is sort of the core infrastructure with the job scheduler, with the interfaces, with all the various data storage engines. And then built on top of that core are various systems such as SQL, or Spark's complement to Hive, machine learning, graphs, streaming, all sorts of different stuff. And again, this Spark is really young, so I'm sure a lot more of these little squares up top will pop up. And then the other cool thing is Python, Scala, and Java are first-class citizens in Spark. So it really opens it up to a larger audience. And then R is sort of in the works, but not exactly production yet. And so this is another view of Spark and how it fits into the existing ecosystem. And so what you'll notice is, okay, this one doesn't work. But so we have Spark, the core engine here, and then we have all of the various systems that I've showed on the previous slides. But you can also see that Spark works on top of the existing Hadoop infrastructure, such as HDFS. Yarn can also go here. And then you have as a complement Hadoop, MapReduce, Hive, Storm, and all of the Hadoop ecosystem. So when we talk about Spark, it's not really either Spark or Hadoop. They can work in the same system, and it's really about picking the best system for the job. So just a little more about RDDs. So the way RDDs were described in the paper were a read-only collection of objects partitioned across a set of machines that can be rebuilt if a partition is lost. So that sounds like a really simple thing. Strange that somebody would write a whole paper about it and then become famous. But doing this in memory is really difficult. And RDD became the abstraction that allowed Spark to support in-memory caching, whereas it wasn't able to be easily done in Hadoop. But the other really nice thing that RDDs offer is a really expressive and familiar Scala collections API for doing big data analysis. And that's what I'll be focusing on in this talk, not the in-memory caching aspect. And for those of you who are functionally inclined or love Scala Z, another way of looking at RDDs are a monadic expression of lazy transformations, except RDDs aren't monads. And if you didn't really understand any of that, don't worry, it'll become clear. So I'll be giving a demo of how to use Spark to show you what RDDs are capable of. And then I'll be diving into what an RDD actually is. And in order to do that, I'll be using the Spark shell. So the Spark shell is really cool. It's built on top of the Scala shell. And what it allows you to do is perform large-scale queries interactively. And you'll see that. And it's just amazing for prototyping or really just analyzing your data in a very quick manner. And the other nice thing is you can run Spark, you can point Spark shell at your local host and it'll spawn multiple threads to analyze your data, but you can also point it at a yarn cluster. So you can be issuing commands to thousands of machines in your yarn cluster to perform analysis. And same for mesos. And it has all the advantages of the Spark shell, such as static type checking and autocomplete, because it really sucks when you had a job running for hours and then turns out you have a syntax error. And as you'll also see, Spark really shows off why Scala is different and why it's really useful compared to, let's say, Java or a couple of other languages. And in this specific case, you'll see how Spark makes really interesting use of lambdas to create a really concise API for big data analysis. So just going back to our previous diagram, I'll jump through most of these components. So we'll be looking at the core Spark API first. So here's a basic Spark shell. And I'll just walk through it quickly. We load a text file from the Spark context, which is what SC stands for. So SC just contained, for example, the authentication for HDFS, how to connect to Yarn, whether it's local or not. So just the execution context. And then we just load up a text file called titles.txt, which is on my computer. But you can also just throw in an HDFS link, and it'll load it out of HDFS. And when you see this, it almost looks like we're just working with a in-memory Scala collection. I mean, we just flat map over it. This is your just general word count example. So we just work through the list of titles. We flat map it to extract each of the words out. We map it into a tuple of the first word and then an integer so that we can reduce over it and sum over the last part so that we get a count per word. And then here's just more filterings and sort bys. Again, syntax is extremely similar to Scala, but in the background, all of this can be running in parallel on thousands of machines on a Yarn cluster. So, I mean, despite how simple the API is, it's doing a lot of work in the backend. So now I'm just going to open up the Spark shell and just run these commands. And so this is on a vanilla Spark installation. So really not doing anything special here. So, okay. So I just loaded up the list of titles and well, this is a bad example. So these are Wikipedia titles, and unfortunately, the first one's a little. Probably should have looked at the data. So we'll blur over it in our recording. But this is what it looks like. Let's just do. Let's just do. And you can see a little more, but it gets better. Unfortunately, all the weird ones are first since it's sorted alphabetically. So, anyways, going on, we're just going to define tokenize, which splits a title. So the titles are separated by underscores. Each word within the title is separated by underscores, so we're just going to split it. And so we'll get a list of words. And so, for example, if we pass in this input, we get this as a title. And now we define another function called cleanse. And what this does is it removes all the weird characters. It removes really any other character, any non-alphanumeric characters in lowercase it, so that when we do our reduce, you won't have like a different word for a capitalized word versus a non-capitalized word. And again, just to show you what that does, we pass in a word with a capitalization, a comma at the end, and it just spits out a lowercase word with all the characters, all the special characters from that. And so now comes the actual use of Spark. And so when we loaded the title into the titles variable, it created an RDD. And so what we did here is we just call flat map tokenize, and then we cleanse each word, and then we reduce it and we catch it. And now this happened really quickly. And we're actually working on a pretty decent data size, about 6 million titles. All of the titles in the English Wikipedia. So what happened here is that nothing actually happened other than to Spark aggregating a lot of these computations to run later. So, So now when we actually run count, this is, so what I did was I ran the first command first, and then I ran the second command. Now the second command is slightly different than the first command. It has this collect at the end, which means that we'll perform all of these calculations on these remote machines, but then pass it all onto the local machine. And what collect will do is cause the entire computation to be run. And what you'll see is once we call collect, it returns back a list of all the word to count mappings as tuples. And this is just a more printable view list. So that's pretty cool. We were able to, I guess, do a pretty large-scale computation. Again, instead of titles being 6 million lines, imagine it being hundreds of millions, if not billions of lines. And these computations, instead of being scaled out to threads on my own machine, being scaled out to threads on Yarn. And you can see why this API is really powerful despite how simple it is. And so, yeah, a core principle behind the RDDs is that you have two different sort of functions. One is a transformation, which all it does is it transforms the data in some way. So either mapping it, or joining it, or sorting it in any manner. And then, so when you apply transformations, Spark doesn't do anything. It just aggregates those transformations inside the RDDs. So that then when you perform an action command, such as asking, hey, can I have everything in these RDDs on my local computer? It knows the entire graph of those transformations and can optimize it so that it can avoid a lot of extra work. So that's the gist of the Spark API. Again, it's just really straightforward. There's really not much to it, and it looks surprisingly like the collections API. So now we want to show you why RDDs are really interesting. And so I'll be demoing the Spark SQL API next. And it's again, it's complementary to Hive in the sense that they're trying to accomplish similar things, which is being able to execute SQL on large collections of data in HDFS. So here's a quick demo on what it takes to create a schema in Spark SQL. So we initialize some context for SQL. Don't worry too much about what that does. And then the interesting thing is we don't have to define our schema at all. All you have to do is define a case class containing the column names and the column types. And Spark will automatically infer the column names and types so that you can do SQL queries over it. So super cool. A lot of magic happens in the background. So what we do here is, previously, we have a tuple of all the counts from the word to, well, the word itself, and then how many times the word appeared in the titles file. And so we just turn that into a case class via this map function. Again, at this point, this is all RDDs, so this is all still operating on potentially remote machines in your cluster. And then what we do here is, now that we've imported this SQL context, we just added a ton of new functionality to RDDs, specifically SQL DSLs, such as where, select, and select. So now you can perform SQL operations in a DSL manner on RDDs. And again, this is really cool because we haven't done much work here. All we did was really turn an RDD into a, turn an RDD into a collection of case classes, and we were able to query the RDD with a SQL DSL. So yeah, I'll just demo this. So start context, SQL context, and then I define the case class here. And now I turn my previous counts from tuples into case classes. And now what I do is execute a SQL DSL on it. And as you'll see, it outputted 116, which is the number of times Scala, the word Scala appeared in the Wikipedia title. So, pretty cool. So, the DSL is nice, but I think a lot of people still prefer text queries. And it's, again, really trivial to load RDDs or transform RDDs so that they can support text queries. So all we do is we just call register temp table on our RDD, give it the table name, and now we can just call this SQL function that was imported from the SQL context, pass it in just a SQL query, exactly matching the SQL query, the query we expressed in the SQL DSL from before. And then we call again collect on it, so it'll execute it. And so these two are exactly the same. And what Spark SQL does in the background is it'll parse the SQL and then transform it into the Spark Core API, something that can be executed in the Spark Core API. So very similar to what Hive does when it takes in SQL and then converts it into MapReduce jobs. Again, I'll just show that real quick. So we register our table, and now we can just execute. They can't be on separate lines. So again, we get 116 back. And just to execute the So this is the what the SQL query gets turned into, and again, the same Scala, the same Spark API that I was showing you earlier, the Spark Core API. So, well, okay. And so Spark SQL can actually do a lot more. So the next thing is, well, what if we want user-defined functions expressed in Spark SQL? Well, that's really easy. You just call register function, give it the function name, and then what you want the function to do. And then you can just refer to it in your string SQL. So as you see, we define length, which calculates the length of the string. So now in our SQL query, we can query for all words with a length of 10. And then there's a couple other statements to show that it supports most of the SQL statements. So you have your order bys, limits, et cetera, et cetera. And again, what it ends up getting turned into is a Spark Core API query. So the other thing to note is, we made our query RDD here. We didn't call collect, so it didn't actually execute anything. And now what we can do is, this is still an RDD, so you can still apply all of your other transformations on it, such as map, filter, all of that. So the Spark Core API is all still there. And this is extremely powerful because previously, at least in the Hadoop ecosystem, all of these infrastructures are separate. So when you query for something in Hive, you have to save it into HDFS and then read it out of Hadoop MapReduce jobs. Now all of your computations can be together in a single file. And what makes it even better is none of this has to be persistent intermediately onto HDFS. So you get huge performance increases since this all just lives on the memory of your executors. And so all we do here is simple map. We map so what we query for is all words of length 10 sorted by the number of occurrences. And so we just want to display what those top 10 words are and how many times they appeared in the titles.
Can I ask you a question?
Sure.
In transformations, do you have the ability to append?
Yes, that's actually exactly what's going on here. Is until you call an action, like collect or save it to a file, nothing happens, so you can append to it as much as you want. And then what Spark will do is once you call an action on the RDD, and as I'll show later, the RDD knows all the actions prior, all the chained actions to it, and then it'll do its fancy stuff and schedule the jobs accordingly as execution passes. So again, just a quick demo. I'm going to register the length function. And so again here I didn't execute the SQL, and in fact what it printed out was just a execution plan, much like you notice from I guess more SQL. And then query RDD is what we get back. It's just an RDD of the SQL query. And so we just map over that, and then we call a .collect on it, so the job actually runs, and as you'll see, we get a count of all the words with 10 characters and the number of appearances in the titles, sorted by the number of appearances.
So one question is for each, does it do that in parallel or is it sequential?
Good question. So let me go back. That's actually a good distinction. So one of the problems, or one of the things you'll run into initially with Spark at least, is the Spark's API is so similar to Scala Collections API that sometimes you just accidentally start running like these huge computations on your main driver by accident instead of parallelizing it. So the thing to know is anytime before you take an action or call an action command such as collect or any of the things I listed, nothing happens. So anything before that gets distributed parallelly. in parallel. But once I call collect, it pulls everything down into the main Spark driver node, which has a scheduler and everything else on it. And now, so when I call for each on it, it runs it locally, so it's not parallelized. So yeah, you do have to be careful about that. Good question.
So what was the answer? Was it running in parallel or?
For each was not, but everything else above collect was. So for example, the word filtering, length, the sorting, the limit, and then the map here also.
So the intermediate operations are running in parallel by default?
Yes. So the intermediate, that's correct. So the intermediate operations are as if, let's say you wrote up Hadoop MapReduce jobs and it was distributed to all the machines.
So is it possible to remove the collect and put for each? Or I have to put the collect?
Yes. So you can actually call that for each. For each is also an action. So I actually left the collect here because so far collect has been the action, so I wanted to clear domaining. But yeah, you can also do dot for each println and it should do something
And it
similar.
will give this exact behavior.
Yep.
Okay.
Yeah. Okay.
Question.
Sure.
Is there any kind of query optimization going on here?
Yeah, there's a lot of optimization going on here. So for one, Spark doesn't execute any of these steps until you call the last action. So for example, I don't know how detailed I should get, but shuffles are really expensive in Hadoop. And there are certain cases where you shuffle the data around so that in between stages, so that you get better partitioning. And so what Spark will do is it'll create a graph of these jobs from what you passed in through the RDDs. And it knows when to, for example, not do shuffles, or when to even perform multiple steps on the same machine, so that everything is in memory already. And again, this is, for example, when you just call a simple map, if you just chain multiple maps together, there's no reason that has to be split up into multiple stages. Versus if you call a join, that requires, I guess, shuffles and a lot more work to be done. So hopefully that sort of answers your question.
Partially. So in particular, I was wondering, in your first example, you first collected the popular words, and then you filtered ones whose length was more than 5 symbols. So would Spark be able to push that filter to before even grouping them?
No, it's not that smart, unfortunately. So the core Spark API may not be able to do it, but if you look at Spark SQL, I think Spark SQL has its own query optimizer. So I think it does that, although the query optimizer is still a little immature, as in you can probably read through most of the code and see exactly what it does. So there's still work to be done there. But again, it's a much harder task because you're working with distributed computations here.
Question? Yeah.
Yeah.
So can you explain what kind of use cases you have found which you're not able to do with Hadoop and you are using Spark, and also if it is a real-time kind of thing, so are you able to process streaming
Yeah.
data?
Can we? I'm actually right about to get to that. So let's okay, last question.
Is the print line if you say this text file, is that done in parallel, or is that also a serial operation?
So everything after collect. So when you call collect, Spark just turns the RDD into an memory array. So anything after that.
Not correct. So instead of print line, if you save as text file, is save as text file a serial operation, or is that done in parallel?
It's serial because after the collect is made, it's just all collect does is it says, give me all the data in this RDD in array format on the local machine.
You don't need a collect to save as text file.
No, you don't. So if we go back, one of the one of the action is save as a text file too.
So if you don't have a collect and just you save as text file, is that a pattern of yours?
Yeah. Especially if you do it into HDFS. I don't know what. I think if you put a local path there, it'll just save the text file onto each of the individual nodes, which you do not want to do.
Can I ask you one more dumb
Sure.
question? You said that you are looking at streaming data because you are doing often interactive analysis.
Yep.
Now, if there is streaming data, the RDD file has to change.
Yes, that's a really good point, and I'm right about to talk about it, because streaming is a whole different paradigm. You're completely right. So we can't do any of this, or at least it can't. We have to do more. And that's what Spark Streaming is all about, is we have the core Spark API, but there just needs to be more infrastructure to handle streaming data. So Spark Streaming, it complements Storm, so very similar tasks. You have a stream of incoming data, and you want to do pure, almost real-time analysis on it. And similarly, you want all of this to be fault tolerant. So Spark handles that for you. It'll take the input stream and copy it onto multiple machines so that, if the machine parsing the stream fails, it can move the jobs onto a different machine. And another interesting thing is, and this is getting more specific, is when you have streaming data, typically the only way, you still have to partition it somewhat. The smallest being, each individual data point to larger batches. So what Spark Streaming does is it batches the data into RDDs. But another interesting use case is, in a lot of cases when we do streaming, you want to do longer-term computations, such as how many times did we see this hashtag within the past hour, but we want to know that value on a per minute basis. So you need some sort of window for, I want this to run X number of times per minute, but I also want the window to be X size, and those are very different values. So, so what Spark will do is, when you, and I'll show you the API real quick, is when you do a filter, or when you do any sort of transformations on Spark streaming output, which is called a D stream, which is a batch or collection of RDDs. Those RDDs are split into your time intervals plus the whole window. So, for example, if your time interval is a per minute run, you can have a window that's 60 minutes. So each batch will have 60 data points or 60 RDDs.
It's a snapshot, but still not the entire data.
Right. Yeah. So going back, input format. I guess it's pretty much what everybody uses. Kafka uses HDFS. So with HDFS, it just constantly detects if you've added a new file, and then it'll push that file in. Yeah, so, and again, the API is really simple. So Spark Streaming has a special utility for Twitter because that makes demos really nice and easy. But again, as you can see, at the end of the day, we still get back a set of RDDs that we can do our transformations on. So that's what this filter is about. But as you'll see, in this case, we also want so 5 seconds is how big the windows are. Really straightforward, very minimal work. And so that's Spark Streaming. Again, I'm just going over streaming, graph, and MLib really quickly since I still haven't talked about RDDs yet. But this is just to show you how RDD can be extended in these various sorts of ways for these different use cases. So next, we're going to talk about GraphX, which is a parallel to Graph from Hadoop. And so what GraphX does is you pass it in RDDs containing tuples of the vertices and edges. And it'll optimally partition and index your graph so that you can do traversals and various algorithms quickly. So offers an API to combine join graphs and traverse them. And it also has just predefined functions that you can run on a graph. Page rank, connected components, triangle counting, so just pretty useful. And again, it's really easy to do it's really easy to do. So you make a graph out of your nodes and your links. And then once you have a graph, you can just call that page rank on it and get the vertices out, which again are just RDDs. So ranks is just an RDD. And so typically when you do these large graph transformations, you want to minimize the data stored in each node. Since again, you want a lot of this to be able to fit in memory. So we'll typically leave out the label so that the nodes are just an integer. So what we can do then is, because ranks is just an RDD, we can just read out the labels from a text file, put it into another RDD, and then join the two RDDs together. And then at the end of the day, what we have is the page ranks with the vertice IDs joined by the IDs in our text file. So again, just because of the fact that GraphX returned RDDs, we were able to do this operation really easily, and again in a single file, single workflow. Okay. And last of all, there's MLib, which is a machine learning library, and it serves a similar role to Mahout. And so, as many of you who probably have used Mahout have realized, the Mahout runs really slowly, depending on which algorithm you pick, especially the iterative ones. And the reason being is Hadoop will save intermediate computations onto HDFS, which is a really expensive computation. So machine learning is actually one of the best use cases for Spark right now, where you can easily see performance increases of 10x or more. And again, it makes sense because instead of saving into a network store in between each computation, it all already lives in memory. And so it's a pretty new library, so it doesn't have the full set of capabilities that Mahout has, but it's still a decent amount. And again, they're working on adding a lot more. So you have your regular statistical functions like mean, variance, regressions, decision trees, clustering, principal component analysis, gradient descent, and again, all of these are parallelized. So again, like Mahout, it's really nice that machine learning experts put in the time of creating these libraries for you so that you can just run it easily on a large data set without really knowing how it's implemented in the back end. And this is what I was saying earlier. Machine learning is just a great use case for Spark because the algorithms tend to be iterative, so you really get a lot of bang for the buck for the in-memory caching capability.
Yeah, a quick question about MLib. So has its own library, or is it wrapper on top of Mahout?
It's its own library.
Okay, and does it have random forest, and what is the data, minimum data set we need to make use of this? I mean,
yeah,
useful.
I'll actually show you. So the data set are, again, all expressed as RDDs, as usual. So again, it really depends on what you're training over, right?
Yeah, I suppose I'm trying to, so is there any minimum, like 1 gigabyte or like 500 gigabyte? What kind of data set would be a good use? Like,
oh, I see.
If I take 100 byte,
Yeah.
that makes sense. So I'm saying about the size of data, basically.
So there's no reason why you can't run a 500 megabyte computation on it, but
No,
yeah,
I should be
there
able
are.
to do it, but I'm thinking,
Okay.
what is the minimum I need? I mean, when I'm trying to do some project, it's not a very big data set, it's just for learning.
Oh, I see. Yeah, so here's the thing, at least from my perspective, is what's stopping you from using a overkill system like Spark on a smaller data set is how you interact with it. So for example, Mahout takes a lot of work to set up. as well as the rest of the Hadoop ecosystem, whereas you can just download Spark, run it locally, and you get access to all of this. So in some sense, there's no reason not to use it for a small data set, but if performance is critical, I'm guessing you're going to be able to get much better performance out of more non-distributed systems focused on it. And I can't tell you a specific number because I think it definitely ranges across the board, but I would say like easily, yeah. And
for learning.
and I think that's a great point in that the API you use here are very similar to the collections API, which can be considered small data. So it really lowers the bar for the amount of effort it takes to take advantage of a large system such as Yarn and the Hadoop infrastructure from a programmer's perspective or developer standpoint. So this is a sample MLib demo. And so again, we load some data into an RDD. And so this is a linear regression example. These are just X and Y's. So we have training data, which we turn into a case class of labeled points so that we can feed it into the linear regression training model. Again, really simple, X and Y. And when we feed it in, we just pass it in our parse data and then the number of iterations, and we get back a model. And now what we want to know is, well, how accurate is our model? So then what we can do is we go back to the original parse data, and then we map all the points and just call a predict, so model.predict on it. So use our model to predict the same points that we already have. And then what we can do is just do some simple math and calculate the mean squared error to get a general sense of how.
So usually you will have a test, like from the data set you will divide it to two, like 80% as a test and 20 as a training.
Yes, not in this case. So you're talking about validation.
Right.
But in this case, we're not doing validation. We're just calculating mean squared error, which shows us how good of a fit the linear regression is. So for example, our data may not be linear, in which case we'll get a mean squared error, like a high mean squared error.
Excuse me. Can you do algorithm pipelining with dispersion?
I'm not familiar with algorithm.
So, say for instance you have Dempster Schaefer and then K-means plus 3. You want to take the output of your Dempster Schaefer and put it into K-means plus 3.
You can. So that's one of the big wins of Spark 2 is you have all of these libraries that has input as RDD and output as RDD, and all of these RDD have this unified API, map filter, and all of that. So to answer your question, yes, you can.
And is this 1.1 or 1.2?
I don't think, well, we might be talking about different things then, because what I thought your question was just, let's talk offline about it, because I think you're asking about something slightly different and pretty specific. Yeah. Okay. So I just gave you guys a quick tour of the entire Spark ecosystem, starting with the base Spark API and the variety of different systems built on top of that Spark API to support unique workloads, such as streaming, graphs, and SQL. So now that you've seen RDDs in action, I want to go back and talk about how RDDs are implemented. Because again, it looks like a lot of magic in the front end. You can just call map on something, and it'll parallelize everything for you, put it onto Yarn, all of that stuff. So pretty much what I talked about. This was my slide from earlier. And so to take that monad example a bit further, for those of you who understand monads, you can almost look at an RDD as a monad that encapsulates an iterator. So at the core of each RDD is the data that's associated with it, and it's expressed as a lazy iterator that you can call .map and filter. So as you'll notice, all the Spark APIs are functions that you can apply to an iterator. But having an iterator just isn't good enough because we're talking about a distributed system here. So we have to, so an RDD also has to contain metadata about how the data you're iterating over is partitioned. So, for example, without this data, there's no way for Spark to distribute jobs onto multiple machines. And something else that you need when you talk about a system that caches calculations in memory is doing it in a fault-tolerant fashion. So what happens, so for example, if you're not saving intermediate data in HDFS, if that particular machine crashes in the middle of the execution, how do you get all of that data back? So what Spark does is, as you can see from RDD, there's a lot of chaining, there's a lot of metadata. So at any given moment, Spark knows how to reconstruct all the steps into where it failed from the original data set, which is how it's able to avoid storing intermediate data onto HDFS. And again, lazily evaluated in the lab operation expressions.
Because you're not explaining monads and monadic operations. Are monadic operations similar to algebraic operations?
Okay, so it's not monad. So RDDs are not monadic at all in that the flat map definition is just completely wrong. I didn't want to explain monads because I know I can't. So this is more taken as, if you know monads, this parallel might be useful, but if you don't, then don't worry about it. Yeah. Okay.
And can it do something like, you know that if there's a failure, you don't want to have to repeat more than 20 minutes worth of work or something? Is there a way of storing the state?
So yeah, this is a feature of Spark that I don't talk about in my talk, but there's a concept of checkpointing. So you can do something similar to what Hadoop does and save intermediate data into a reliable store such as HDFS. But the idea is to not do it at every single step since that's costly. Okay. So here's a visualization on this how RDDs get executed. So you have, so here's the RDD query. We have a join, we have a group by, we have a filter, and then we're doing a pass. So the join, we're joining the top two boxes into, and the group by, and then the filter operation is right here. So as you'll see, from an RDD perspective, it's just a directed acyclic graph of computational jobs that it has to do. So for example, in order to do this step, Spark needs to perform both of the jobs above first. So that's a lot of what the scheduler handles. But what you see here are just single RDD objects. And again, it abstracts around the entire distributed nature of your computation, which is splitting each of these tasks onto thousands of machines. So in fact, what you actually have is each of the RDDs containing multiple partitions, and the various transformations, such as your maps, are executed on each of the partitions, and then passed on to the next RDD. So how does that happen? And so it turns out an RDD is a really simple thing. It's just an interface in Spark so that Spark's job scheduler and the engine can execute these tasks. So in order to define an RDD, you need to define, let's start here. So I'm just going to go ahead and jump into my IDE and go to rdd.scala inside the Spark source code. And so what you'll see here, that's not my other window. Okay, so what you'll see here is this is the abstract class RDD. And here are the 3 things that various RDDs implement. So compute, which is the actual computation that's being done. So if you're calling .map with a function, it'll have .map there. And then partition is how you want to partition your data. So for example, for HD, if your data is in HDFS, then the most sensible partition scheme is partitioning the data into HDFS blocks. And then dependencies is what stores all the historical information. So what you saw in the graph in my previous slide, where you can follow a child RDD all the way back up to its parent to be able to recalculate all the data if it's lost. So yeah, all it is are these 3 functions. And so let's just walk through some examples. So when we call .text file to load a text file from my local computer into an RDD, the RDD that it generated is called a Hadoop RDD. And so a Hadoop RDD generalizes over text, but it can also obviously support HDFS blocks with special optimizations for it. So in the case of the Hadoop RDD, the compute is just reading the HDFS block or a section of the file. If, for example, if you have like a multi-gigabyte file, Spark will automatically split it into, let's say, 1 gigabyte chunks so that you can easily run parallel computations over it. And so get partitions is what defines a partition split. So Spark will either do it at the file level or split it HDFS block, and there are no dependencies because it's the source. And in fact, we can look at Hadoop RDD. And I lost my mouse. There's a lot of stuff going on here, but you'll see there's get partitions, which is pretty simple. It just looks at the Hadoop input format splits and partitions accordingly. And then you have the compute, which just reads the file from HDFS or from your local machine. And then get dependencies, again, doesn't really matter here. So now, when we call a .map on the RDD that we received, it returns a mapped RDD. So that mapped RDD contains the computation for that map. So it contains the function that you're mapping over and the fact that you're mapping over something. So for the compute part, it has to compute the result of the parent RDD. So it calls .compute on its parent, and then it just calls a .map of containing the function of the result of the parent computation. And then for get partition, it just partitions accordingly to its parent. So for example, if you're calling a .map on a Hadoop RDD, it just partitions across the HDFS blocks. And then get dependencies, it's just a single dependency on its parent. So it's just a one-to-one relationship. And again, so the mapped RDD is surprisingly simple. So I'm going to go to the map function on the RDD. So that's the function you actually call when you call a .map in the Spark API.
The number of partitions is the same as the number of executors?
Yes, it tries to be. I mean, you can have more partitions than executors if you run out of executors. But yes, if there are enough executors for partitions, then they should be equal. So we just call map, and as you see in map, we pass in a function that we want it to be mapped over, and all Spark does is it creates this new map RDD passing in the function. So So clean is a bit of an implementation detail because, in your function you might have a closure, so you need to close over all of your variables and send it over the network, or else the variable you're referencing in your closure won't be available on these remote machines. So that's what clean does, is it packages up this function nicely. So when we go into the Mac RDDs, there's nothing special. Get partitions, we just get the partition of our parent node. We always assume there's only one. And then for compute, we calculate our parent, and then that returns back an iterator that we just call .map with a function over it. So really nothing fancy going on here. Really surprisingly straightforward. Okay. So then we have the code group RDD, which is what happens when you call join. Again, when you call compute, now it has to do a lot more work. It has to calculate each of its parents, shuffle it, and then combine the RDDs of its shuffled, combine the shuffled RDDs of its parents. And then get partitions is just one per reduce task, which is a configuration variable that you pass in. And the dependencies is each of the parents that you're grouping on or joining on. Okay. So in summary, RDDs is the abstraction that allows Spark and the various systems built on top of it to offer developers a really clean, nicely unified API that also allows all of these systems to interoperate with each other. One of the big wins here is because it's in Scala, and the fact that it's jobs run really quickly, you can do interactive analysis on really large data sets. And it has amazing Hadoop integration. So for example, Spark is not officially supported at eBay, but because we have a Yarn cluster, and we can just point Spark to our Yarn cluster and everything works, even though there is no explicit support for Spark. And again, because it's able to leverage in-memory caching to squeeze a lot of extra performance out. Again, references, these slides will be posted online, so these are things to check out on the original Spark paper, a couple talks on it, and then RDDs that you should look into. And that's all. Thank you.
So, since it's very memory oriented, the RDDs and the execution and stuff, does it require a lot of infrastructure support? Like, okay, how many memory needs to be on the machine?
Yeah, that's a good question. So I'm actually talking to infrastructure people at PayPal to acquire larger machines with much larger memory to support Spark workloads. So that's definitely true, although you can just run it on a regular Hadoop cluster and not really get much of a performance hit because it will just spill over to disk. And the nice thing about Spark, there's a graph on it, but even if your entire computation cannot fit in memory, you still get incremental speedups if parts of it can fit in memory because Spark will make certain optimizations.
I had a question. A couple of slides ago, you were showing some code.
Yes.
And in that, before that, where there is a line which says that compute a new RDD with a new operation.
I don't think
There was a bunch of stuff.
So this is
No, not this one.
Later?
Actually, after. That's actually.
okay. Well, do you want to just look at it offline then?
Sure. But my question is,
Okay.
does an operation change the RDD?
No, so RDDs are immutable.
Okay.
So when you call a .map on it, it just generates a new RDD
Okay.
with a link to the parent one.
Okay.
And immutability is just huge in the distributed systems because there's no way you can sync all of this.
And if you lose it, you can recover it because you have parental.
Yeah.
Okay, thank you.
So you mentioned MPI support on one of the slides. Is it possible to have like an imputation DAG where one of the steps is an MPI step? So for example, I imagine some of the linear algebra operations common in machine learning are probably implemented much better in BLAS than in anything you can do in MapReduce 1.
Yeah, so that's definitely possible, and that's, so I would encourage you to look at the Spark SQL code, because they have to do something similar, right, where they have to take a SQL query, and it's not just a one-to-one translation. There's a lot of room for optimization in the execution plan. So they do some tricks with how they call get dependency and stuff like that, so that it's executed in their own way outside of Spark.
So it's executed without using Spark's shuffle for grouping by.
Yep.
Okay.
Yeah. We can, again, talk offline. Feel free to shoot me an email if you're wondering how that works.
I had a question about the spillover of disk, actually.
Okay.
If you start fucking around searching with the right combination of keywords, you end up in tons of threads where people are complaining about out-of-memory error, Java heap space error, and so on. And my question to you was if actually the RDDs would handle something that can't fit in memory, so it would just take part of it and memory would keep the rest of the disk. Or...
Yeah, so there are optimizations in that regard. So it will try to put iterative stuff in memory so that, in the simplest way the caching works is it's the least recently used. But I believe there are optimizations so that if you're iterating over a ton of stuff, it will keep it